Hello, hello. Okay, let's resume our reading. Traversing linked lists, and I think we read this before, I just lost my spot. Now you know how to declare, initialize, and manipulate a linked list in the kernel. This is all very well and good, but it is meaningless if you have no way to access your data. The linked lists are just containers that hold your important data, and you need a way to use lists to move around and access the actual structures that contain the data. The kernel, thank goodness, provides a nice set of features for traversing linked lists and referencing the data structures that include them. Note that unlike list manipulation routines, iterating over a linked list in its entirety is clearly an O of N operation for N entries in the list. Okay, so kind of getting back to where I was, we know that we could iterate through a list using this list for each macro. And then you have other helpers. I think there's like another one called a list for each entry here. Okay, so that's what we kind of emulated that approach in the last video, writing this list head thing from scratch. So I'll move on away from that, and then I'll probably do, let's do iterating through a list backwards, and this, I think, okay, yeah, so we're getting close to moving on. Okay, so iterating through a list backwards. The macro list for each entry underscore reverse works just like the list for each entry, except that it moves through the list in reverse. That is, instead of following the next pointers forward through the list, it follows the previous pointers backwards. Usage is the same as with list for each entry. So you're going to pass in for each entry, or you're going to pass in this function call to list for each entry reverse the temporary pointer to contain your list head, the head of the list, and then the member. Okay, so I think what ends up happening is that if you pass in the head, you'll just go to the previous, and then you can just go backwards from there. Pre. So there are only a handful of reasons to favor moving through a list in reverse. One is performance. If you know the item you are searching for is likely behind the node you are starting your search from, you can move backwards in hopes of finding it sooner. A second reason is if ordering is important. For example, if you use a linked list as a stack, you can walk the list from the tail backward to achieve last in, first out ordering. Okay, so stack wise. So if you do not have an explicit reason to move through the list in reverse, don't. Just use list for each entry. So only move through the list backwards when you really have to. Iterating while removing. The standard list iteration methods are not appropriate if you are removing entries from the list as you iterate. The standard methods rely on the fact that the list entries are not changing out from under them, and thus, if the current entry is removed in the body of the loop, the subsequent iteration cannot advance to the next or previous pointer. Okay, so this is kind of saying that you shouldn't mutate the data structure of the list in weird ways as you are actually iterating through. Otherwise, you're just going to wreck everything. And I think this is like a proper practice. So this is a common pattern in loops, and programmers solve it by storing the next or previous pointer in a temporary variable prior to potential removal operations. So that's only if you really want to do it. The Linux kernel provides a routine to handle the situation for you. List for each entry safe. So you use this version in the same manner as list for each entry, except that you provide the next pointer, which is of the same type as pause. The next pointer is used by the list for each entry safe macro to store the next entry in the list, making it safe to remove the current entry. So let's consider an example again in iNotify. So void iNotify, inode is dead. It actually does this. So the next pointer is this one. And oh, so yeah, so it'll store the next node in this pointer here that you provide. Okay. So this function iterates over and removes all the entries in the iNotify watches list. If the standard list for each entry were used, this code would introduce a use after free bug, as moving to the next item in the list would require accessing watch, which is destroyed. If you need to iterate over a linked list in reverse and potentially remove elements, the kernel provides list for each entry safe reverse. So this is the reverse version of this safe version. Where is it right here? This safe version here where you provide that next pointer. Okay. So the usage is the same as with list for each entry safe. Okay. So warning, you may still need locking. So the safe variants of list for each entry protect you only from removals from the list within the body of the loop. If there is a chance of concurrent removals from other code or any other form of concurrent list manipulation, you need to properly lock access to the list. See chapters 9, an introduction to kernel synchronization, and chapter 10, kernel synchronization methods, for a discussion on synchronization and locking. Other linked list methods. Linux provides myriad of other linked list methods, enabling seemingly every conceivable way to access and manipulate a linked list. All these methods are defined in the header file linux/list.h. Okay, so if you need to do something with the linked list, this is the place to go and look at. Okay. So queues. Queues, a common programming pattern in any operating system kernel is producer and consumer. I wouldn't even say like operating system. I think in general, in programming, do you have a producer, something that produces data and sticks that data into the queue, and the consumer goes into that queue and picks up that piece of data and does stuff with it. It's like publisher, subscriber, you know. Event-based things are also like that too. I mean, the event emitter is the producer, and the thing that's subscribing to the event would be the consumer. So in this pattern, a producer creates data, say error messages to be read or networking packets to be processed, while consumer in turn reads, processes, or otherwise consumes the data. Often, the easiest way to implement this pattern is with a queue. The producer pushes data onto the queue and the consumer pulls data off the queue. The consumer retrieves the data in the order it was enqueued. That is, the first data on the queue is the first data off the queue. So first in, first out. For this reason, queues are also called FIFOs, short for first in, first out. See figure 6.5 for an example of a standard queue. So NQ is going to put data into this list here. DQ is going to take the oldest thing that was placed earlier, like way back, first in, first out, and do stuff with it. So it's like assembly line. The Linux kernel's generic queue implementation is called Kfifo, and is implemented in kernel/kfifo.c and declared in Linux/kfifo.h. This section discusses the API after an update in 2.6.3.3. So we're in 2.6.3.4, so it's okay. Usage is slightly different in kernel versions prior to 2.6.3.3. Double check Linux kfifo.h before writing code. Okay. So let's read this first, and then we can go and like kind of quickly look at the decorations and the implementation of it. So, Kfifo. Linux's Kfifo works like most other queue abstractions, providing two primary operations. Enqueue, okay, unfortunately named in, so it's actually called in code. Dequeue, which is actually called out in code. So the Kfifo object maintains two offsets into the queue, an in offset and an out offset. The first in offset is the location in the queue to which the next enqueue will occur. The in offset is the location in the queue to which the next enqueue will occur. So that is the place where the next element is going to be placed into. The out offset is the location in the queue from which the next DQ will occur. So that is going to be, the offset is going to be that address where you're going to pop, or not pop, like take stuff out of the queue. So the off offset is always less than or equal to the in offset. That makes sense, right? So it's always, at the worst, if you had a queue here, okay, this is in offset, and this is still out offset. Whereas like in another situation, in offset, out offset. Oops. So really, at most, they're equal to each other. That's what they're talking about. And I think the worst case is that they're both null. So it wouldn't make sense for it to be greater. Otherwise, like the in offset would not make sense for it to be greater. Otherwise, you could DQ data that had not been NQ'd. Okay? So the NQ, or in operation, copies data into the queue starting at the in offset. The NQ, in operation, copies data into the queue. Copies data into the queue starting at the in offset. When complete, the in offset is incremented by the amount of data in queue. So if it's like a struct of persons, it will increment by basically the size of one struct of person, one person struct in this case. The DQ operation copies data out of the queue starting from the out offset. When complete, the out offset is incremented by the amount of data enqueued. Whoa. The DQ operation copies the data out of the queue, okay, starting at the offset, out offset, and then when complete, the out offset is incremented by the amount of data in queue. So it starts, so grows what, downward? Upwards? When the out offset is equal to the in offset, the queue is empty. Okay, let me try to read this again. The NQ, or in operation, copies data into the queue starting at the in offset. Okay, when complete, the in offset is incremented by the amount of data in queue. So if it's like 0, and then it'll be like 10, for example. And then if the DQ operation copies data out of the queue starting from the out offset. Let's just say it's also at 10 in this case. When complete, the out offset is incremented by the amount of data in queue. When the out offset is equal to the in offset, the queue is empty. Oh, okay. That makes sense. Okay. No more data can be dequeued until more data is enqueued. Okay, so I had this picture wrong, I guess. Where is it? This one. It doesn't work that way. I think they're just literally numbers. So in offset, out offset. So if they are equal, that means they're empty. So that means I've added 10, added this amount of bytes, and I've also removed this amount of bytes. So that means if I enqueued again like 10 more bytes, I could end up with in offset being 20. Okay, and then out offset is still 10. That means I've only taken out 10. So then if I were to take something out again, this can turn to 20, and that's again an empty queue. And I can just like add more, right? Whoops, 50. And that will give me 3 more elements. And since I'm like 50 divided by, 50 minus 20 divided by 10, it's going to be 30 over 10. This gives me 3 elements away. All right. So when an offset equals to the length of the queue, when the in offset is equal to the length of the queue, no more data can be in-queued until the queue is reset. Okay, so let's look at Kfifo. Kfifo.h. Okay. Okay, Kfifo initializer. So it's a struct size s. So you actually need to provide the size. Oh, here we go. The struct will help us right here. So we need to provide the size. We have a buffer of bytes. That's why it's called unsigned char. Then we have offset int. Okay, data is added at offset. Okay, data is extracted from offset. Okay, so far so good. Just a struct. Kfifo is a struct. So it would be the kfifo.size, kfifo.buffer, things like that. So here's how we declare one. Let's see, macro to declare a Kfifo and the associated buffer. Name, the name of the declared Kfifo data type. Size, the size of the Kfifo buffer. Must be a power of 2. Note 1. The macro can be used inside a struct or union declaration. Note 2. The macro creates 2 objects, a Kfifo object with a given name and a buffer for the Kfifo object name. Okay, so we create a Kfifo buffer and a Kfifo name. Struct Kfifo name. Oh, okay, so this is the Kfifo itself. And this one is the name of the Kfifo. Okay. Sure. Init Kfifo initializes a Kfifo declared by declare Kfifo. So this is initializing. And what does that do? So init Kfifo initializer. So that's probably going to do a malloc, this function. Let's see. Well, not malloc. Oh, no, it doesn't do a malloc. Oh, size S. Buffer B. Okay, so that was what? Buffer B was literally this thing here. I don't know what this double thing is. Actually, let's do this. Let's yank that. And then, wait, does this actually go to my clipboard? Let's see. And then let's do, let's do, let's do AI. Let's see. Oh. Dang it. I don't have it. It's okay, we'll check it later. So define Kfifo. Okay, whatever. Let's see. Reset out is probably going to, okay, so they make it equal to, make it empty. Kfifo size returns so the Kfifo pointer will just return back to size. Okay. Oh, cool. Returns the number of used bytes in the FIFO. So, what is this? Doing some math, right? So, out will be the FIFO out. I think this is just some like synchronization thing, and then you just do in minus out. Was that what we did? Return the length. So I did, what is it? In, right here. Minus out, okay. And now it's like 3 elements. Okay, that math checks out. Kfifo is empty. Basically checks to see if in and out are equal. And then check if it's full. Well, if this length is equals to the size, that's fine. Okay, this is actually not too bad. There's some like syntax that I'm not familiar with, but yeah. Let's see, add out. Ooh. Add out in turn. Also add the add offset. So basically increment the out, and add in will increment the in, sure. And then what is this? Calculate the index to offset. That's fine. Peak. Determine the length of the next record in the FIFO. Peak n. Okay. Poke. Storing the next record. The length of the next record. Sure. Okay. Kfifo in rec puts some record data into the FIFO. Okay, so this is in queuing. So in queuing will be Kfifo in generic. So what is this? This function copies n bytes from the from. Okay, so right here, pointer to some arbitrary piece of data into the FIFO and returns a number of bytes which cannot be copied. So yeah, on the good scenario, it has to be 0. A return value then greater than n value means that the record doesn't fit into the buffer. Okay. So given this FIFO, given some piece of data, given some what is this? The length of the data. Okay, so given the length of this, and then the size of each one of these record, right? No, the size of a record field. Sure. We want to do Kfifo in generic. Okay. And then the out is probably opposite. Sure. Get some record data from the FIFO right here. Out rec. Sure. Okay. So if I did, oops, kfifo.c, maybe there's more implementation there. Kfifo init. Oh, so this is replaced right here. Pre-allocated buffer. All right. Kfifo alloc allocates a new FIFO internal buffer. So that's the buffer. Allocates code to allocate the buffer. Okay. Out data. Oh, this will actually bring data out. So I think it'll put into the 2 pointer, and then this one actually will stick it into, it looks like to the FIFO buffer. Cool. Anyway, just trying to make sense of things. Okay, creating a queue to use Kfifo, you must define and initialize it. As with most kernel objects, you can do this dynamically or statically. The most common method is dynamic. So we'll have int Kfifo alloc. We'll pass in that Kfifo struct, the size that we want, and I don't even know what this is. GFPT. Let's see. This function creates and initializes a Kfifo with the queue of size bytes. Makes sense. The kernel uses the GFP mask. What is this? GFP mask to allocate the queue. We discussed memory allocations in chapter 12, memory management. Okay, fine. So they're saying, don't worry for now. Upon success, Kfifo alloc returns 0. On error, returns a negative error code. The following is a simple example. So given this struct FIFO here as a Kfifo struct, int return is going to be either what? Upon success, it returns 0. So it should be 0. And if it's an error, it'll be negative. So if return ret, which is going to be, if it's non-zero, meaning it's error, return that value. Otherwise, what do we do? Oh, that's it. If you want to allocate the buffer yourself, you can do void Kfifo init blah. Okay. This function creates and initializes a Kfifo that will use the size bytes of memory pointed at by the buffer for its queue. With both Kfifo alloc and Kfifo init, size must be a power of 2. Statically declaring a Kfifo is simpler but less common. This creates a static Kfifo named name with a queue of size bytes. As before, size must be a power of 2. Okay. When your Kfifo is created and initialized, and queuing data into the queue is performed via the Kfifo in function. So we saw something like this. Okay. This will be the data you want. This will be the size of that data, and the 0 Kfifo. So it's actually easier to use. I think we were looking at the harder, like, internal stuff. This function copies the len bytes starting at from into the queue represented by Kfifo, or by FIFO. On success, it returns the number of bytes in queued. If less than len bytes are free in the queue, the function copies only up to the amount of available bytes. Thus, the return value can be less than len or even 0 if nothing was copied. Okay. Dequeuing data. When you add data to a queue with Kfifo in, you can remove it with Kfifo out. So same type of function. This is the pointer to which you want to point to that piece of data when you've pulled it out. This function copies at most len bytes from the queue pointed at by FIFO to the buffer pointed at by 2. On success, the function... Oh, so it's already allocated. It's allocated buffer already. Okay. So just that's the reason why I was doing the mem copy. That's the reason why I was doing mem copy. Okay. I think it's somewhere. Copy from user. Right here, yeah. Oops. Yeah. Something like this. Okay. Makes sense. Okay. So yeah, this function copies at most len bytes from the queue pointed at by FIFO to the buffer pointed at by 2. On success, the function returns the number of bytes copied. If less than len bytes are in the queue, the function copies less than requested. When dequeued, the data is no longer accessible from the queue. Okay, when dequeued, the data is no longer accessible from the queue. That means we have it into our buffer already. Sure. Okay. Yeah, this is the normal usage of a queue, but if you want to peek at data within the queue without removing it, you can use Kfifo out peek. So use this if you want to kind of see what's at the like the first thing to pull out from the queue, but you don't want to pull it out yet. This works the same as Kfifo out, except that the out offset is not incremented, and thus the dequeued data is available to read. Oh, okay, so it still copies everything to that buffer. Okay, thus the dequeued data is available to read on a subsequent call to Kfifo out. The parameter offset specifies an index into the queue, specifies 0 to read from the head of the queue as Kfifo out does. Okay, so obtaining the size of a queue. To obtain the total size in bytes of the buffer used to store a Kfifo's queue called Kfifo size. Static inline unsigned Kfifo size. Given this FIFO struct here will give you back the size. But that size is represented as the total size in bytes of the buffer. Okay, not like the number of elements. I think that's represented by length. So, yeah. In another example of horrible kernel naming, use Kfifo len to obtain the number of bytes enqueued into a Kfifo. Holy what? Okay, so I thought len was the number of elements, but this Kfifo len is the number of bytes enqueued in Kfifo, whereas Kfifo size is the total size in bytes of the buffer. This is the how many bytes have been enqueued. This is the okay. To find out the number of bytes available to write in the Kfifo called Kfifo avail. To find the number of bytes available, so based off of how much you have left in the size, Finally, Kfifo is empty and Kfifo is full, return non-zero if the given Kfifo is empty or full respectively, and 0 if not. Wow, okay. Gotta be careful here. Kfifo len is just basically the number of bytes enqueued in Kfifo. Kfifo size is going to be the size of the buffer in Kfifo. Okay. I think this will be like the in offset then. Anyway, similar to that. To reset a Kfifo, jettisoning all the contents of the queue, call Kfifo reset, static inline void Kfifo reset. To destroy a queue Kfifo allocated with Kfifo alloc, call Kfifo free. Okay, given this Kfifo, it'll free up memory. Sure. If you created your Kfifo with Kfifo init, it is your responsibility to free the associated buffer. Okay. How you do it, because I think that's because we had to pass in that buffer, right? Maybe. How you do so depends on how you created it. See chapter 12 for a discussion on allocating and freeing dynamic memory. Okay. So, okay. Example queue usage. With these interfaces under our belt, let's take a look at a simple example using a Kfifo. Assume we created a Kfifo pointed at by FIFO with a queue size of 8 kilobytes. Okay, assume we created a Kfifo pointed at by FIFO. So FIFO is our name. With a queue size of 8 kilobytes. So the buffer's 8,000 bytes. We can now enqueue data onto the queue. In this example, we enqueue simple integers. In your own code, you will likely enqueue more complicated task-specific structures. Using integers in this example, we see exactly how the Kfifo works. So given some sort of integer we want to enqueue, okay, we're going to just enqueue 32 times. Given this FIFO, the integer pointed at by, because it's a void pointer, and then the number of bytes of that element, which is going to be 4. So the Kfifo named FIFO now contains 0 through 31 inclusive. We take a peek at the first item in the queue and verify it is 0. So peek. Okay, given this FIFO, given a pointer val, which is going to be the whatever we're going to peek at stored, and then the size, which is going to be int. So 4. So given that, you should be able to get back some data. Rets it's just the integer, so basically the element. So if it was a struct, this would be a struct. Okay, so we're gonna print with print k. Okay, simple enough. Okay, so to dequeue and print all the items in the Kfifo, we can use Kfifo out. Okay, to dequeue and print all. Okay, so while there's something available, we're just going to dequeue pretty much. And so eventually Kfifo is going to be empty. Okay. This prints 0 through 31 inclusive and in that order. If this code snippet printed the numbers backwards from 31 to 0, we would have a stack, not a queue. All right. Okay. Wondering if it's worth trying to implement this. Probably not. Yeah. Okay. Maps. A map, also known as an associative array, is a collection of unique keys where each key is associated with a specific value. The relationship between a key and its value is called a mapping. Maps support at least 3 operations: add, given the key value; remove, given the key, and then the value, we can just look it up by key. Okay, so although a hash table is a type of map, not all maps are implemented via hashes. Instead of a hash table, maps can also use a self-balancing binary search tree to store their data. Okay, so maps can be like underneath the hood, like not just like an array, like a hash table or like a linked list, but it could also be like a binary search tree. Although a hash offers better average case asymptotic complexity, See the section algorithmic complexity later in this chapter. A binary search tree has better worst case behavior. It's logarithmic versus linear. A binary, because linear, like let's say there's like a collision, right, and you need to do something like, I think it's called separate chaining, whatever, to resolve that collision. There's a potential chance if you implement your like map using like linked lists or whatever, you can traverse like pretty long chain of things. Versus like if you have a balanced binary search tree, everything will always be logarithmic when you search. So a binary search tree also enables order preservation, enabling users to efficiently iterate over the entire collection in a sorted order. Finally, a binary search tree does not require a hash function. Instead, any key type is suitable, so as long as it can be defined with what is this, less than equal to operator. Okay. Although the general term for all collections mapping a key to a value, the name maps often refers specifically to an associated array implemented using a binary search tree as opposed to a hash table. For example, the C++ STL container std map is implemented using a self-balancing binary search tree, so self-balancing, or a similar data structure, because it provides the ability to in order traverse the collection. So the fact that implementing maps with a binary search tree is useful is just because you maintain some sort of sorted ordering. Because remember, like in order traversal is actually sorted order. So the Linux kernel provides a simple and efficient map data structure, but it is not a general purpose map. Instead, it is designed for one specific use case, mapping a unique UID to a pointer. That's the purpose. So some generic pointer, I'm guessing. So if you really think about it, like mapping some sort of UID to just some piece of data, generic data. Pointers to some generic data. So that makes it very flexible, actually. You can store anything. Well, as long as you have the pointer to it, technically. So where it starts in memory. So in addition to providing the three main map operations, Linux's implementation also piggybacks an allocate operation on top of the add operation. This allocate operation not only adds a UID value pair to the map, but also generates the UID. The IDR data structure is used for mapping user space UIDs, such as iNotify watch descriptors or POSIX timer IDs, to their associated kernel data structure, such as the iNotify watch or the KI timer structures, respectively. Following the Linux's kernel scheme of obfuscated and confusing names. Okay, let me do this sentence justice. Following the Linux kernel scheme of obfuscated, confusing names, this map is called IDR. You never would have guessed IDR is called map.